Hello everyone, Mr. Minix, my name, math is my game. Today in my Algebra 2 class, what we're looking at is solving systems, solving systems of linear equations. It's been a weird start to the year because we haven't really officially gone through much of Chapter 1, and we haven't really officially gone through much of Chapter 2, and we haven't really officially gone through much of Chapter 3. And we have this big unit test coming up, and today's lesson is more of a exhibition. Anybody ever hear of an exhibition? Anybody ever go to a boxing match and watch an exhibition boxing match? You know what that means? It means that there's two people are fighting, but there's nothing at stake. For you, what's at stake is kind of a review of these techniques and kind of a lead into tomorrow what we're going to do and why we'll appreciate how awesome the calculator is. So by the end of this lesson, what you should be able to do is to remember or recall solving systems by the following methods. There's several methods of solving systems. One of which is the substitution method. The substitution method. Another method is by graphing. Another method is by graphing. Can anybody recall a third technique that you learned about in Algebra 1 or maybe even geometry? Anybody ever go to the doctor and you had gut problems? This might sound kind of gross, but anybody ever go to the doctor with gut problems? You know what they call going to the bathroom when it's not just a number one and at the doctor? You're getting rid of waste that was in your system, right? It starts with an E. A lot of letters. Anyway, the elimination method. The elimination. Whoa, I can type. It's the elimination method. Elimination. When you eliminate waste. Some people call the elimination method linear combinations. Some people call that linear combinations. In the past, I used to call it something else, but I better not tell you. I better not tell you what I used to call it in the past. Unless you really wanted to know. Maybe we don't want to know. All right. So that's what we're going to do today. We're going to solve systems by graphing, by substitution, by elimination, or linear combinations method. And I want to put a thing here, special systems. Special systems. Okay. Special systems. We got to figure out how to handle those because there's some systems that are special, that are different, that something weird happens. Okay. So that's kind of a roadmap of where we're heading. If you've witnessed some of my lessons, you'll probably recall I like to start off with a definition. Makes sense. So the first thing I'll do here is define what a system is. A system of linear equations. A system of linear equations is simply two equations using the same variables. That's the definition. A system of linear equations is simply two equations using the same variables. Oh. One word that I left out, it's optional, but I'm going to say it's a set of two equations. I forgot the of. a set of two equations using the same variables. Okay. So to see what that looks like, we might have something like y equals x plus 2. And we might have something like y equals negative 3x minus 2. And the reason I mentioned set, when I mentioned set, there's a grouping symbol that I need. Anybody remember what grouping symbol you need when we talk about sets? Not brackets, not parentheses, but that other one. Braces. You need a brace. Okay. And the interesting thing is, even the TI Inspire knows that. When you use the TI Inspire to solve systems, it even puts the braces up. Now, it's weird that there's a brace on the left. A lot of times, we don't bother with the brace on the right, but technically it's there. But sometimes math people get lazy and they don't put the one on the right. If you're OCD and you got to have the one on the right, then I'll put it. Shout out to anybody who's OCD. I probably shouldn't do this if you're OCD, because that's probably bad. Or that, or that. So, enough of that. All right, a solution. A solution to a system. To a system of linear equations, is one of two things. So the solution to a system of linear equations, a solution, come on, wake up. A solution to a system of linear equations is one of two things. It's the ordered pair that satisfies not one, not the other, but both equations. It's the ordered pair that satisfies not one of the equations, not the other equation, but both equations. When I say satisfies, I don't mean, ooh, I like what you do to me, you x and you y value. That's not what I'm talking about. I'm talking about making it true. I know that was kind of creepy, I'm sorry. But satisfies in this context means it makes it true, okay? The other way to look at it is it's the point where the graphs of the equations meet. The graph, where the graph of the equations meet. See if I can get all that recognized. So the point where the graphs of the equations meet, that's supposed to say of the equations, not on the equations. So the point where the graphs of the equations meet. Okay. So that's pretty much it for the definitions. Everything from here on out is just going to be examples. I've got some systems written on the sideboard. We're going to be looking at each one. We're actually going to look at that first one. And we're going to see if we can't solve this. So we're going to try to find the point where the graphs meet. We're using loud graph paper or quiet graph paper? Anybody have a preference? Which graph paper? No preference. Example 1, let's try to graph. Let's solve by graphing. Let's solve by graphing. Solve by graphing. The system is y equals x plus 2. And y equals negative 3x take away 2. So that's our system. It's that first one we looked at. It's the first one we looked at. We're going to try to solve it by graphing. And solving by graphing, I think, is pretty straightforward. You graph. And you look at the graph and you try to see where they intersect. So let's see. y equals x plus 2. Anybody remember where you could start when you go to graph that thing? The 2 on what axis? On the y-axis, because that's my y-intercept. Okay. So then what do? I got to look at the slope, and the slope is 1. So from that point that I plotted, I can rise 1 and run 1. So I'll go bam, 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 bam. And when I'm doing these, I like to fill in as many of these points as I can. And after having graded some of your quizzes, I noticed that some of you did this on your quizzes when you graphed, and that's good. That's fine. There's nothing wrong with that whatsoever. But what you got to realize is there is also a smooth line connecting those points. So when it comes to the domain, that function, not only does x equal -10, but x equals -9, and x equals everything in between them too. So I'll talk more about that when we get the quizzes back. This other equation, then, we'll do the same thing. Y equals -3x, take away 2. So we're going to look at its y-intercept, which is -2, and we're going to look at its slope, which is what? The slope of this blue one here is it's a -3. So from there, I'm going to go down 3 and over 1. Did I go down 3 and over 1 the right way? Did I go down 3 and over 1 the right way? Why? How do you know it's not the right way? Slope's negative. The line should be falling from left to right. So I guess I kind of screwed that one up. There we go. That's better. Down 3 and over 1. Now see, here's where, if you just take one more little step. Do you see those 3 blue dots that I got? If I keep on trucking, I'm going to find my intersection point real clear, right? Real clear. Up 1, 2, 3, and over. Hey, there it is. There it is. 1, 2, 3, and over 1. There it is. Bam, 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 bam. So my answer, my solution, is that point. It's that point. But we probably ought to point out what the coordinates are. The x coordinate there is -1. The y coordinate there is +1. So if I plug in those values into both equations, it ought to make both of them true. Let's see if it makes this one true. Is 1 equal to -1 plus 2? In other words, is 1 equal to 1? Sure it is. Makes that one true. Let me check the other one. Does it make that one true? In other words, is 1 equal to -3 times -1 minus 2? Is 1 equal to 3 minus 2? Is 1 equal to 1? Sure it is. So there we go. That's it. That's how we can solve that system by graphing. What do you think? Easy? You remember doing that? Good. That might take a little bit of work, and what we're going to do on tomorrow is we're going to see another way to use the calculator to do this. And I'm going to go ahead and solve this with the graphing calculator if it'll let me. You know that there's a lot of latency between my calculator and this, but I'm going to try to graph it. Y equals x plus 2. And then tab y equals -3x minus 2. Graph that. Now, it would be real nice if I could view a lined grid. Watch what I'm going to press to view a lined grid. I'm going to go menu. I'm going to go view. I'm going to go grid. Grid, I said grid. I said grid. And lined grid. I think it makes that pretty easy to see what the answer is now, right? Then I would have to go menu, analyze, intersection, click over here, click over there, and there it is. Okay. So are there any questions, comments, concerns, short debates, long debates at all about example number 1 solved by graphing? Going once. Going twice. If not, what we're going to do is we're going to look at example 1 again. Example 1 again, but this time with substitution. And the reflexive property. Everybody thinks the reflexive property is dumb. They're like, it says A equals A. That's so dumb. That's pointless. Why do we need to say that A equals A? Well, I'll show you why. The reflexive property says that A equals A, right? So that also means that B equals B. And that also means that C equals C. And that also means that D equals D. And that also means that E equals E and F equals F. Anybody picking up what I'm putting down? And G equals G. You can stop me whenever. And H equals H, and I equals I, and J equals J, and K equals K, and L equals L, and M equals, and M equals M, and N equals N, and O equals O, and P equals P, and Q equals Q, and R equals R, and S equals, no, I don't think you do, nobody said it yet, and S equals S, and T equals T, and U equals U, V equals V, W equals W, X equals X, Z equals Z, but Y equals Y, doesn't it? Since Y equals Y, X plus 2 equals negative 3X minus 2. Oh, I never thought about it that way. The reflexive property actually has some meaning to it. It's not just something stupid that says something equals itself. There's a meaning to it. So I'll go ahead and add 3x to both sides. So I'll get 4x plus 2 is equal to negative 2. And I'll subtract 2 from both sides, and I'll get 4x is negative 4. And I'll divide by 4, and I'll get x is negative 1. And I know my answer is going to have to be an ordered pair, xy, and x is negative 1. Interesting thing about the substitution method is it involves substitution. Twice, in fact. So then if I wanted to get my other value, I guess I'm going to have to substitute that back into one of these equations. So my y value is going to be negative 1 plus 2, which is 1. So of course my answer is negative 1, 1. So that's one way that we could use the substitution property. Notice with the substitution technique, notice though you substitute twice when you do that method. All right? Okay. Sometimes people say that I go a little too fast when I solve equations. How was that pacing there on that one, all right? Good? Okay. Good. Well, let's look at example 2. Or I'll leave that up there another minute. Maybe somebody's still jotting that down. There's a different kind of substitution technique that requires us to maybe sometimes solve one equation for one variable in terms of the other. And it's weird because it ends up you have to use the distributive property and you have to be good at it. Example 2. Solve by substitution this system. Y equals 2x minus 5 and 4x plus 2y equals 6. So when we go to solve this one with substitution, we're probably going to have to substitute twice. We know that that's what y is equal to. Would everybody agree that that's what y is equal to? The highlighted stuff? Because that's what y is equal to, we can take that highlighted stuff and we can put that highlighted stuff into the other equation in the place of y. And that's the whole idea behind the substitution method. So the way that substitution method works then is we would take 4x plus 2y. And that's equal to 6. What's going to take the place of my y, though? Yeah. The first equation's stuff that y is equal to. This whole quantity of 2x minus 5, right? That quantity of 2x minus 5. In math, a lot of times we use the word quantity, and some people are like, dude, why are you saying that word? It's confusing me. It's because it's an expression that we need to put in parentheses. You'll hear me say this a lot this year. Quantify quantities. Quantify quantities. If you ever have to square negative 1, Some people would read it -1 the quantity squared. That means they put parentheses around it like that so they get the answer right. So the point is, make sure you quantify quantities. This 2x minus 5, that's a quantity, and we do want to quantify it, so we want to put it in parentheses, just so we don't forget to distribute. Okay. So the 4x is still 4x. We distribute, and we're going to get another 4x minus 10, and that's all equal to 6. Four x plus 4x, that's going to give me how much? 8x. So I'm going to get 8x minus 10 is 6. So I'll go ahead and have to add the 10. So I'll have 8x is 16. So I'll divide by 8. So x equals 2. So my answer is going to be 2 something. 2 something. How do I get the y value? Yeah. Got to plug the x value back in again. So I'll go back up to here, plug the x value in. So my y value is going to be 2x minus 5. So that's going to be 4 minus 5. What's my y value there end up being? -1. Awesome sauce. Could I have solved this by graphing? Could you have solved that by graphing? Do you know how to graph that second equation? Would you have been able to graph it? Some people are good at graphing that second equation, some people might not be. You know, Ed Bassmaster says sometimes you just got to look at it. Do we want to look at it and see if we could have solved that by graphing? Let's look at it and see if we could have solved that by graphing. Example 2, solve by graphing. So this is again, right? So this is y equals 2x minus 5, and 4x plus 2y is 6. Oh man, I don't know if I got the skills to do this. I don't know. The first equation's easy. The first equation is y equals 2x minus 5. That's easy. Minus 5, up 2 and over 1, 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 and up 2 and over 1, and down 2 and over 1, and down 2 and over 1. That's not bad. But it's this other equation, this 4x plus 2y equals 6. I don't know if I could graph that. Anybody have any ideas what you could do? Dear math gods, please send me an angel to put this into slope-intercept form. So subtract the 4x. So 2y equals -4x plus 6, and then divide by 2, and divide by 2, and divide by 2. So then y would equal -2x plus 3. That's an excellent idea. Nice. What made you think of that? Okay, you did these in your. Okay. Well, I'm not spending 2 months. I'm spending 1 day on it. So, so y equals -2x plus 3 would start here, down 2 and over 1, down. Oh, look at that. There it is, down 2 and over 1. There's our solution. The whole point of that exercise wasn't to waste another 5 minutes. It's that you can solve a system in more than one way. If you haven't heard me say this, I say it all the time. There's more than one way to the Eastwood Mall. I would take Warner Ravenna Road to 5 and 82 to West Market Street to 422. That's how I go to the mall. You might take 305 to 5 and 82 to 82 to 46. Maybe you don't even know where the Eastwood Mall is. Fun day you will. Here we go. Example 3. Example 3. Solve by elimination. By elimination. This system is awesome. It's already set up perfectly. 2x plus y is equal to 6, and negative 2x plus 5y is equal to 9. Oh man, this is so awesome. Whoever came up with this system could not have been any more generous. If you recall with the elimination technique, what we try to do is we try to take the two equations and we kind of look down these vertical columns like this. And what we want to do is add vertically down those columns. So if we end up adding the first column, our 2x plus our negative 2x, those cancel. And the x's go away. That's awesome because we get to the answer almost directly, almost right away. So in our second column, y plus 5y is going to give us 6y. 6 plus 9 is going to give us, how big is that? 15. So my solution here, my y value is going to be divided by 6, divided by 6. Y is 15 over 6. Now I could reduce that. Good thing we spent a week in class going over fractions. They're both divisible by 3, right? So 15 divided by 3 is 5. 6 divided by 3 is 2. So the y coordinate is 5 over 2. 5 over 2. How can I get the x coordinate? Go to the store and get one of those Glades things that makes it smell fresh. What are those Glade things called? The Glades plugins. I'm going to go to this first equation. Doesn't matter which one you use. I'm going to go to this first equation and say 2x plus y plus 5 halves equals 6. So I'm going to need to get my 6 in terms of halves. So I guess I'll multiply 6 by 2 halves. So I've got 2x plus 5 halves equals 12 halves. So I subtract 5 halves from both sides. Boy, it's a good thing we had that fraction lesson. So 2x is 7 halves. So I divide by 2, which is like multiplying by 1/2. So my answer ends up being 7/4, 5 halves. I know some people freak out when they see the fractions. They're not that bad. They're not that bad. So we saw the substitution technique, we saw the graphing technique, and now we see this elimination technique. How do you feel about the 3? All right? Wouldn't it be awesome if there was a much faster way? There's 3 much faster ways. Doc, insert, calculator page. I want to go back to that last example, and I want to try solving it on my Inspire. You might want to jot this down in your notes if you can. How about menu? So from a calculator page, and I'll even write this up too. From a calculator page, from a calculator page, from a calculator page, from a calculator page, from a calculator page. We're going to go menu. Option number 3 is algebra. So menu, algebra. And then option number 2, look at option number 2. Do you see what it says? Solve system of linear equations. Dude, that's awesome. Solve systems of linear equations. That's so awesome. And then you just follow the prompts. Then you just follow the prompts. Okay, so you're going to go menu, algebra, solve systems of linear equations, and then you follow the prompts. Boy, I wrote that really sloppy. Menu, algebra, solve systems F. Solve systems F of linear equations. All right. And then follow the prompts. And then follow the prompts. Okay, so let's see what that looks like. How many equations? 2. The variables are x and y. Okay, that's good. That's good. Okay. Oh, look how it put the braces. Do you see that? That's pretty neat. We're going to just go right back to that last example, if the calculator lets me in here. Come on. Wake up. So I got 2x plus y is 6. 2x plus y is 6. And then the second equation, negative 2x plus 5y, negative 2x plus 5y equals 9. And so I end up with what I ended up with. That's pretty fast. Dude, that's way easier. Did your Algebra 1 teacher show you that last year? Or geometry teacher show you that on the Inspire? There's something that's faster than that we're going to look at tomorrow. Any questions, comments, concerns, short debate so far? Okay. Well, let's look at example 4. Example 4, solve 2x plus 4y equals 10, negative 16x minus 32y equals 20. I notice I didn't say by what method. I didn't say by what method. What method would we like to try? Yeah. Which one? The elimination? That makes sense. Did you say elimination? Makes sense to me. So for elimination to work, we need to have these numbers here have the same coefficients. And unfortunately, they don't. We need to have these numbers here have the same coefficients, and they don't. But we could get that. I better remember what to do. Multiply the top equation by 8. What we're going to do is we're going to multiply the top equation by 8. So what that's going to give us, 8 times 2x is going to give us 16x. 8 times 4y is going to give us plus 32y. 8 times 10 is going to give us 80. And that's that first equation now. The second equation is going to be what the second equation was. Negative 16x minus 32y equals 20. Now, if I go ahead and add these, let's see what happens. This is awesome. This is awesome. What happens to the x's? They cancel. Now, when they cancel, what number's left in its place? Something plus its opposite equals 0. Good. So we end up with 0 here. What about the y's? They're also going to cancel, and we end up with 0. And what's 80 plus 20? 100. So what this is trying to tell us is that 0 is equal to 100. Do you believe that? So we got to interpret this. This is kind of like going to Spanish 3. Hola, señores. ¿Cómo está usted? ¿Dónde está el baño? ¿Cuántos años tienes? Me llamo Mateo. ¿Cómo se llamas? ¿De dónde eres? ¿Qué tiempo hace hoy? ¿Cuál es la fecha hoy? La nariz, la frente, el brazo. We got to interpret this answer. We need an interpreter. Please, somebody help us. What does that mean when we get something that's not true? Yeah. How'd you know that it meant no solution? From last year? Okay. What do you think this is going to look like when we graph it? You're right, it's no solution. Good one on you. If I were to take this first equation and solve it, I'll get 4y is negative 2x plus, was that 10? 10. And I'll get y equals negative 1/2 x plus 5/2. So that's what that equation is if I solve it. If I solve the second equation, I'm going to get negative 32y equals 16x plus 20. And I'll get y equals negative 1/2 x plus 5/8, plus 5/8, plus 5/8. What do you notice about those two equations there? And what do you notice about them? Same slope. And are their y-intercepts the same or different? Different. So what's going to happen with two lines with the same slope? They're going to be parallel, and they're not going to intersect. So these won't have any answer. So the deal is this one is no solution. So that's one of your special systems. Anytime you get a false equation, anytime you arrive at a false equation, it's going to be no solution. You're going to have lines that don't meet. You're going to have lines that do not intersect. Now, I wonder what that's going to look like on the calculator if it's going to say no solution. Maybe we better check that. Maybe we better check that. So I can press menu, algebra, option number 2, bouquet. My first equation was 2x plus 4y, and that equaled 10. My second equation is negative 16x, take away 32y, and that equals 20. And let's see what this says. I'm curious. Oh, it says no solution. Well, that's awesome. That was nice. So we kind of got bailed out by the calculator there. Example 5, last one. Solve. I always save the best for last. I'm like Vanessa Williams like that. 3x minus 6y is 12. And y equals 1/2 x minus 2. Sometimes these are already set up real nice for the elimination method. Sometimes they're already set up nice to graph. What's this one set up perfectly to do? Which technique? Substitution, I think. Right? Because we already have y solved. We already know that this is what y equals. So we could say that 3x minus 6y is 12. So in place of y, we're going to put 1/2 x minus 2. I wonder what's going to happen here. Oh, I wonder, doom, 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 doom. I don't know what to say after that. That was a song from the 50s. 3x, let's see, 6 times a half is 3. That's minus 3x. So those are going to cancel, which is going to leave 0. Minus 6 times minus 2 is going to give me plus 12. So 0 plus 12 is equal to 12, is equal to 12. So 12 equals 12. Hey, there's a reflexive property again. Duh, of course 12 equals 12. What does that mean? Anybody remember this one from last year? Yeah. There are infinitely many solutions. And what we're going to do, this is Algebra 2. We're going to take this one step further. The answer in Algebra 1 is that there's infinitely many solutions. That was good enough in Algebra 1, but this is varsity math, son. I know some people don't like it when I say son, but this is varsity math, son. What we need to do is we need to figure out where the answers are. So our solution set is really as follows. It's the set of any ordered pair x and y such that this vertical line here, this means such that. That means such that. So my answer is going to be any ordered pair that's on the line. Now I just got to pick one of these equations. Which equation do we like? 3x minus 6y equals 12 or y equals 1/2 x minus 2? Which one do we like? Take your pick. First one or the second one? Second one? Okay. Y equals 1/2 x minus 2. What this is saying, let me see if I can get my highlighter going. Highlighter, here we go. What this says is that the answer is any point on that line. The answer is any point on that line. From a visual perspective or a graphing perspective, does anybody know what happens here? What's going on? Earlier, we had the idea to solve one of the equations for one of the variables. What happens if we take this equation and solve it? We'll get negative 6y is negative 3x plus 12. So we'll get y equals 1/2 x minus 2. Wait a minute. Wait a minute. What's the deal with those equations? They're equal. They're the exact same. They're identical. And so if we graphed the lines, it would be two lines that are the same line. So does the answer make sense that the answer is any point on the line? Here's what I want you to watch out for. Here's what you got to watch out for. If you use this TI Inspire, there's going to be some times where it's not going to tell you that there's infinitely many answers. Watch what it tells you. Let's see, 3x minus 6y, I said minus 6y, equals 12, and I know it says a half, and or 11, and y equals negative control divide fraction, 1/2. Oh, geez. This is going just swell. So there's the 12, there's the 1, there's the half, and I got x minus 2, x minus 2. I'm real curious to see what the calculator's going to say here. Did I punch something in wrong? Oh, I know what I did wrong. Anybody see my error? I got a negative sign on this slope. Should just be 1/2. There you go. What the heck is that? 2c1 plus 4c1? That doesn't make any sense. Do you see why it's necessary to know more than one way to solve these things? Does that make sense? Well, that's it. I hope it's been real and it's been fun and it's been educational. Might not have been the most exciting lesson in the world, but hopefully it's a good reminder of special systems, solving by graphing elimination, and substitution. Tomorrow I'm going to show you a faster way still to solve those with the calculator. So tomorrow when you come to class, grab a calculator. Have a nice day. Good.